Hello and welcome back to Introduction to Number Theory. In this video, we will discuss the set of remainders modulo p, where p is a prime integer. Well, we know that this set consists of 0, 1, 2, and so on, p minus 2, p minus 1. We can introduce, we know that we can introduce operations of adding remainders to one another and multiplying remainders and all this modulo p. And this will turn the set of remainders into a field. We denote this field by fp. And let me just write that sum and multiplication is considered also modulo p. This is a field. And in this field, let's consider a polynomial, the following polynomial: x minus 1, x minus 2, and so on, x minus p minus 2, x minus p minus 1. So you may have noticed that this polynomial is the product of all brackets of the form x minus one of the elements except for 0. Well, it's obvious that all these elements are zeros of this polynomial. But do we know another polynomial which turns into 0 when x is substituted by one of these numbers, one of these elements, by any of these elements? So such a polynomial that applied to 1, 2, and so on to p minus 1, it turns into 0. Well, it turns out that we really know such polynomial. It is x to the power p minus 1 and minus 1. Because according to Fermat's small theorem, this is congruent to 0 for all non-zero remainders x. Since we're living inside a field right now, these two polynomials, both of degree p minus 1, both of them, have the same, since they have the same sets of zeros and the same coefficients upon the greatest power of x, here it is equal to 1 and here it is also equal to 1, then these two polynomials are simply equal as polynomials. This means that if you take this expression and take all the brackets and multiply all of these elements to each other while expanding the brackets, you will receive simply x to the power p minus 1 and minus 1. There is an interesting corollary of this fact. There are many interesting corollaries actually, but one of them is really important to us. It is the Wilson's theorem. So if we take the minus 1, minus 2, and so on, minus p minus 2 and minus p minus 1, and multiply them, this will be the coefficient of the polynomial upon x to the power 0. And it must be equal to the coefficient of this polynomial, which also does not contain x. So this is equal to minus 1. Of course, equality is inside the field the field formed by the remainders modulo p. How many minuses do we have here? Well, we have p minus 1 minuses. Since p is prime, and we can, of course, separately consider the case when p is equal to 2, but anyway, the number of minuses here is even. And if p is equal to 2, then minus is the same as plus, and in any case, we can say that this expression here is, well, modulo p equal to simply p minus 1 factorial, the product of all integers from 1 to p minus 1, since the number of minuses is even. So this is the Wilson's theorem. P minus 1 factorial. Well, I could write that it is equal to minus 1, but let's return to the set of simple integers. So it is congruent to minus 1 modulo p. Using the same equality of polynomials, you can prove many other interesting properties of elements of the field of remainders modulo p.